All right. So yesterday we were discussing, an argument through which we computed the host of dimension of a Cantor-like set, and I didn't complete the proof yesterday. So I'll just there was one last claim that I made, and then I left it unproved. So I'll just give a reference to that proof. I mean, to this proof. So in case um, if you want to work it out on your own, and if you're having any trouble, then it's theorem 1.15 in the geometry of fractal sets by Falkner. Okay. So yesterday we have seen, we talked about the mass distribution principle. So I'll just refresh our memory. We take an outer measure, mu on E, that satisfies two conditions. The first one is that mu of E uh, is is positive, and secondly, there exists some epsilon such that for all sets, I mean, here I'm considering balls and with small radii. So just a small difference. So okay, the conclusion is that then dimension of E is at least S, right? So I mean, a slight difference from the formulation I had in the last class is that here I am only restricting my attention to balls. Yeah, but we know that in terms of while finding out host of dimension, I can either work with the host of measure or I can work with the spherical host of measure. So if I'm sticking to the spherical host of measure, then the fact that mu grows on balls of radius or balls of small radius in this fashion is sufficient enough for me to claim to conclude that the host of dimension of the set is bounded below by S. Okay. Now, as it turns out, I mean, the way I have introduced this principle, it would seem to at least some of you that it's simply a technique, an artificial step that we introduce to obtain some information about the dimension of the set. But as it turns out, the existence of such measures satisfying, let me call this condition the ball growth condition, okay? Let's say the S ball growth condition or the S growth condition. So the existence of measures that satisfying such S growth condition is innate to sets of dimension S, okay? And this result, I mean, I'm going to state and prove a result called Frostman lemma, which basically ensures the existence of a measure on a set of dimension S that satisfies this condition. Okay. So before stating the lemma, um, let me just introduce this notation. So M of A is the collection of all measures mu, where mu is a Borel measure. And it's with compact support, which is contained inside in A. And it is positive. I mean, it's non-trivial. Oh, it's also finite. So Frostman's lemma states that if I start with an S and a set of dimension S, well, sorry, not exactly of dimension S. Rather, I'm just going to assume that it has a positive S-dimensional host of measure. Is that a question? Okay. Yeah, actually, let me state it in this fashion. For a Borel set A in RT, HS of A is positive if and only if there exists a measure mu in curly M of A satisfying the ball growth condition. Okay. Yes. He has a question.
Doesn't the Hausdorff measure satisfy this? The ball growth condition.
This condition?
Yeah.
Not necessarily. So we know for a fact that if A is, if the S-dimensional Hausdorff measure of A is finite, then in that case, I think the S-dimensional Hausdorff measure restricted to A satisfies this condition. But it's not true for all. I mean, it's not true in general.
Okay.
Yeah. Okay. So, I mean, the measure that you obtain by this theorem is called the Frostman measure. Okay. And it doesn't have to be unique. You know, a set can have more than one Frostman measures. And because of this theorem, I can now, you know, claim or conclude that what should I should maybe as a corollary, I have this result for A in RD, Borel, dimension of this set is equal to the supremum over all S such that there exists a measure mu and supported on A satisfying the growth condition, which I'm going to denote as uh, the growth condition, say GS, because it depends on S as well. Okay. And is this clear why this corollary should be true? Well, I mean, by definition, the host of dimension of A is the supremum over all S, such that the S dimensional host of measure is positive. And now we have shown that it's equivalent to the existence of the Schwarzschild measure. Hence, the corollary follows. So how do I prove this theorem? Right? At least, I mean, one way we have already proved. I mean, that was that the mass distribution principle. If I have a measure satisfying this growth condition, then the S-dimensional host of measure of the set must be positive. Yeah, we had seen that yesterday. And here, yeah, actually, I mean, I can mention that here as well. I mean, I've already said it yesterday. Then is positive, and therefore dimension of A is bigger than or equal to S. Okay, so moving to the proof of the lemma. This direction is already done by the mass distribution principle. So let me start with a Borel set A in RD that has positive S-dimensional host of measure. Now, for this direction, I'm going to make a significant assumption on A, which is that A is going to be compact. Okay, I mean, this proof that I'm going to provide is for compact sets E. So compact sets A. And it's not, I mean, it is a significant restriction that I'm going to that I'm imposing, but there is a theorem that allows you to so given any Borel set A that has positive S-dimensional host of measure, you can actually find out a compact subset of A with positive S-dimensional host of measure as well. So this is, I think, a theorem that was proven by Davis, and so that's quite involved. So I'll not get into that. But with that, using that theorem, I can always reduce the case to the case of compact sets. Okay. So I'm going to make that assumption here that A is compact. Yeah. And so only for yeah. And let the S-dimensional host of measure of A is positive. Let me write dj to be the collection of all dyadic cubes in RD of length 2 power minus j. So these are all the cubes of the form with A coming from the 2 power minus j lattice. And let curly D represent the union of all these guys. So since A is compact, by translating A if necessary, I'm going to assume that A is going to be contained inside one of these dyadic cubes. Okay. Say Q naught in this collection curly D. Now I can introduce this something called the S-dimensional dyadic host of content, which is um, the infimum over all S power of the the diameter of all these QIs, where A is covered by union of QI, and each QI comes from is a dyadic cube. Okay. Now I want you to verify that whenever A has positive S-dimensional measure, S-dimensional host of measure, it must also have positive S-dimensional dyadic host of content. You just have to play around with the definitions of the host of measure to get this. Okay. And once you verify this, if I set, once I verify this, I know that for any dyadic cover of A, the S sum is bounded below by some constant C, which is nothing but the S-dimensional dyadic host of content of A. And this is positive. Yeah. So this is the starting point of our our attempt to construct a measure that satisfies the Ball condition. You have a question?
So there was a small little question from
Yes.
Rani. So
Yeah.
you can read it for yourself. It is kept on everybody. You can read it out. Thanks. Listen.
Right. Oh yeah. So maybe what I claimed earlier might not be entirely correct. So you were asking this question, right, about the S-dimensional host of measure, whether it satisfies this condition. So so Rani is saying that even the finiteness of the S-dimensional host of measure of A is insufficient to say that this condition is being satisfied the S-dimensional host of measure. But maybe, so maybe maybe I'm recalling a different result. But I mean, okay, maybe what I want to say is that um,
Am I audible?
yeah, you are, Rani.
No, I just wanted to say it's directly, we can say that the upper density will be bounded above and below, but not for all R. Like that's the easiest theorem that we can actually say. But if we have to claim that house of measure of A intersection BR of X is less than or equal to R over S for some constant times R over S for all R, I am not familiar with that. Like, is
Yeah,
it?
so you're basically saying that this condition will be satisfied for a range of values of R, not for
Yes,
the whole.
yes.
That's what you're
Like,
saying, right?
and yeah, we can say length sup of IHS of A intersection BR of X divided by R is the bounded below R.
So is that for a sequence of values of R?
Yes, length sup as R tends to 0.
R tends to 0. Yeah.
That is for sure. I know that result, but I'm not aware of anything that directly gives the ball condition.
Right. Okay. Now I'll verify this again. So I'll get back to you. Thanks. Thanks, Rani. Is that clear? The comment. So she's saying that when the S-dimensional host of measure is finite, then you can actually find a sequence of RIs for which this estimate will be held with mu replaced with the S-dimensional host of measure, tending to 0. Yeah. Whether this is being satisfied for all values of R, we don't know. We have to check. Yeah. Yes, yes. No, I will keep that in mind. Certainly, certainly. Okay. So yeah, coming back to the construction of the measure. The measure will be, we are going to, construct the measure as a weak limit of many measures. Okay. And I'm going to introduce a sequence of measures, let's say mu k's, and each mu k is going to be supported inside. What happened? It's fine now, right? Yeah. So, right. Yeah, so we are going to construct, first we are going to construct a measure mu k that will be supported in the 2 per minus k neighborhood of the set A. And then as k goes to 0, you will get a measure that's going to be supported exactly in k. Okay, that's the goal. So the construction of mu k's. We'll start by the dyadic with the dyadic partitioning of RD with the cubes in dk. All the dyadic cubes of length 2 power minus k. And okay, so let me just draw this here. And let's say these are our A's. Or this is the set A. Okay. So each dyadic cube has a length of 2 power minus k. The measure mu k is also going to be defined in a step-by-step fashion. First, I'm going to define something called the mu k1. Okay, so we define mu k1 by specifying what its restriction is going to be on cubes where all these cubes are coming from the kth level dyadic cubes. Okay. So mu k1, I'm going to brute force impose this condition, the growth condition that we require. Okay. So mu k1 restricted to q is going to be 0. Of course, if the cube q is not going to intersect my set A, there is no reason for me to give any mass over this cubes. So it's going to be 0 if q intersected with A is empty. And if it intersects, then I want mu k1 of q to be exactly the length of q power s. Okay, that's the goal. So I'll write this as length of q power s times the Lebesgue measure, normalized. So normalizing will give me length of Q per D in the denominator. Okay. So what is the property of this measure? First of all, observe that the support of this guy is contained inside the union of all the dyadic cubes that intersect A. And these dyadic cubes there are of length 2 power minus k. So the support is contained inside the 2 power minus k neighborhood of A. Secondly, I also see, so that's the first observation. The second observation is that, or see, A, is that mu k1 of Q is exactly equal to length of Q per S whenever Q intersects A. And Q is of course, a dyadic cube of length 2 power minus k. Yeah. In fact, I mean, like, for all other values or for all other choices of Q in this collection, it's always going to be 0. So the inequality, where mu k1 of Q is bounded above by length of Q per S holds for over all cubes in the kth level dyadic collection. That's a Lebesgue measure. Yes. Is it not clear? Okay, then, yeah, I'll just. So it's length of Q to the power S length of Q per S divided by length of Q per D. Because I need to first normalize. So since I'm introducing the Lebesgue measure here, and since I want this condition to hold, I want to divide by the volume to normalize, and then you multiply by the Sth power of the length of Q. Yeah, yes.
Length of Q would mean
2 power minus K.
oh, the side. I thought not volume or diameter. Okay, I see.
No. Yeah. So yeah, in this case.
Oh, 2 to the
so,
minus K.
Yeah, 2 power minus K. Yes.
Oh.
Yeah. I mean, maybe I can just mention that here as well. Here, length of Q is 2 power minus K. Of course, whenever. And this holds whenever Q is in the Q is a 2 power minus K dyadic cube. Right. Now, so this is great. This is good news for us because I've been able to brute force impose this condition. Now, I can check what happens, how much mass is being distributed to other cubes. Yeah. So if I try to compute, if I look at, that's the third observation, for Q1 in, say, dk plus m. So I'm looking at smaller dyadic cubes. Okay. Yeah. Then what happened? Yeah. So if I take Q1 in dk plus m, where m is equal to 0, and if Q is a parent to Q1, where Q is a 2 power minus K dyadic cube, I can compute mu K1 of Q1, right? So, so you see that if Q is not intersecting the set A, then obviously this is going to be 0. Yeah. And it's going to be simply the volume of Q1 times this weight, if that's not the case. Yeah. So it's this weight is length of Q per S divided by length of Q to the power D times the size of Q1 with respect to the Lebesgue measure, which is simply the volume of Q1. So that's length of Q1 to the power D. Yeah. So let us see when this quantity is going to be bounded above by length of Q1 to the power S. Yeah. Length of Q to the power S divided by, oh yeah, well, that's S minus D, right? Times length of Q1 to the power D is bounded above by length of Q1 to the power S whenever length of Q1 is smaller than length of Q, which is the case here. So the required growth condition is, you can verify that it holds for over all cubes of size whose side lengths are at most 2 power minus k. Okay, so it holds for all finer cubes. Yeah. The trouble is we might not be able to verify it for larger cubes. Yeah. And there's nothing special about like there's no reason for me to consider cubes here. I can also look at balls. Yeah. And it's easy to verify. And I want you to verify this, that mu k1 of a ball of radius r will be bounded above by r power s whenever r is smaller than or equal to 2 power minus k. Okay, so this similar relation will hold even when I replace cubes with balls of radius less than or equal to 2 power minus k. Oh, I actually have that, um, you know, uh, that statement written here. So the statement is that if I am starting with a set whose S dimensional, sorry for this, for the diversion, I was just answering his previous question. So if I have a set whose S dimensional host of measure is finite, then I can find a compact subset of this set that again has a finite S dimensional host of measure. And over this set, the restriction of the S-dimensional host of measure will satisfy the growth condition and for all R. Okay. So it's the existence of a subset that is compact. On top of that, the restriction of the S-dimensional host of measure will satisfy the growth condition. Yeah. Yes. I mean, in our problem, no, I mean, so that's a general result. So yeah, here I'm giving you explicit construction, right? I mean, of course, if I prove that, then yes.
No,
Yeah.
difficulty is for large balls.
Yeah.
Okay, that makes sense.
No, I meant even I'm assuming the proof of that is going to take some time. Like I'm just saying that here I'm giving you an explicit construction of a Frostman measure.
Okay.
Yeah. Okay. All right. So as I was saying, I need to. The trouble is.
Have the reference for that?
Yes, I'll write it down at the end.
Yeah,
Yes.
sure.
Yes. Um. So the trouble is to make sure that the growth condition is being satisfied for large balls, right? So yeah, my last observation by a similar argument. you can verify that mu k1 over balls of radius r is bounded above by r power s as long as r is smaller than 2 power minus k and for all x in Rd. Okay. So since I cannot make sure that this condition is going to be satisfied for larger cubes, I'm going to modify the measure. So that's my step 2. So modifying the measure, I get the next measure, that's mu k2. Okay. So here, I mean, for the construction of mu k1, we started with dyadic boxes of size 2 power minus k. And since I want to look at larger cubes, now I'm going to look at the dyadic cubes of size 2 power minus k plus 1. Yeah. So we define, again as before, mu k2 by prescribing what its restriction is for all dyadic cubes of length 2 power minus k plus 1. That will be dk minus 1. Yeah. So how am I going to do this? You may need to change the camera. I'm going to come back to this picture. Yeah. So earlier, we considered, so this, I mean, my A were, it was spread over Rd in this fashion. So I looked at all those cubes that were intersecting A, I mean, which were these cubes. And then I gave some weighted Lebesgue measure or weighted mass. Oh, sorry, weighted Lebesgue measure. That's how I've constructed mu k1. Now I'm going to look at larger cubes. So I'm going to look at cubes of length 2 power minus k plus 1. Let's say I'm looking at this cube. Okay. What I want to do is using the definition of mu k1, I first want to find out what is going to be mu k1 of q. And so this is my new q now, okay? So that's q. If mu k1 of q already satisfies the growth condition, then I don't have any issue. Right? Then I can stick to that weight. So let me evaluate. So mu k1 restricted to q is defined to be, sorry, mu k2 restricted to q is defined to be same as mu k1 restricted to q if the mass of q with respect to mu k1 is bounded above by length of q per s. So I don't change anything here, okay, because I am happy the growth condition is anyway being satisfied for this cube. If this is not the case, I renormalize. So I renormalize and say that this is equal to length of q per s divided by mu k1 of q times mu k1 restricted to q. Okay. So you can see that by renormalizing in this fashion, I have now verified, made sure that mu k2 of q must be equal to length of q per s whenever q lies in this second case. Okay. Again, I'm going to make these comments. So observe first that, see, the support of mu k2 has not changed. I mean, all I am doing here is just changing the weight that is there on mu k1. Yeah. So support of mu k2 is still contained inside the 2 power minus k neighborhood of A. But the uh, additional advantage that I have now is that the growth condition is now satisfied by all cubes that belong to the collection dk minus 1 plus n. So this is to say that this condition is being satisfied all those cubes whose length is at most 2 power minus k minus 1. Yeah. So now I repeat this process. And yeah, so now I repeat this process, and I repeat it all the way up to Q naught. See, I've assumed that A is contained inside one of the dyadic cubes, which is Q naught. And yes, I started with the K. Yes, K is fixed. No, K, so yes, that's right.
K minus 1.
Yes,
So K minus 1 is a bigger square.
it's a bigger square.
Fine. It's concentrated on the bigger square, isn't it?
That's correct.
Now, why do you say that it is still on 2 to the K?
See, here it's a different. I mean, what is the modification? It's still mu k1. I mean, in the first case, it's still mu k1. In the second case, it's just a multiple of mu k1. I'm just renormalizing mu k1 so that my growth condition is being satisfied.
I see.
So I'm just putting more weights into it. Yeah. Is there any other question? Okay. Right. So I continue this process, and I mean I'll continue until I hit the single cube Q naught. Q naught, which contains A. And I started from some level K, so of course I should be able to reach Q naught in finite number of steps. Let me, in addition, assume that the length of Q naught is actually equal to 1. I don't think I need this. I mean, but I'm just going to assume it for just to be on safe side. And after all the renormalizations along this process, whatever measure that I have obtained finally uh, will be called, so that's observation A, B, and that's my third step. Let mu K be the final measure that you obtain. So let's record the properties of this measure now, right? As before, the support of the measure hasn't changed. We are only renormalizing, my original measure mu k1. So it's still contained inside the 2 power minus k neighborhood of A. But the growth condition now is satisfied by a large class of a broader collection of cubes. right? So now this condition is being satisfied by all balls, all cubes of length at least, sorry, at most one. Yeah, I mean, but see, I mean, I have been able to completely cover A now. I'm not going to, so it's zero everywhere else. Yeah. So that means this condition must be satisfied for all larger cubes as well, right? So if, so that means this actually holds for all dyadic cubes Q now. Now, so this is my, yeah, as I've said before, I'm going to construct mu by taking the limit of this mu case. So you can see why I want to take the limit of, as k goes to infinity, because I've now obtained a measure that is supported inside the 2 power minus k neighborhood of A. And, I finally want to obtain a measure that is supported exactly on A. But while I take the limit, it's possible that you may converge to the trivial measure, the zero measure. So what is stopping me from obtaining the trivial measure in this process? So with that in mind, I want to find a lower bound for the size of mu k. Okay. So uniform lower bound on mu k of RD. So how do I obtain this? This is where I have to use the fact that A has some significant mass, which is, given to us by the assumption that the S-dimensional host of measure of A is positive. Yeah. So from the construction, you can actually see that at every step, you are getting a cube so for example, you look at a cube Q in this that comes in the second case of this construction. Yeah. Mu K2 of Q is exactly equal to length of Q power S. Yeah. So if I'm starting with an X lying inside the support of mu K, then I can always find a cube Q, a dyadic cube Q containing X such that mu KL for some L evaluated, the mu KL of Q is exactly equal to length of Q power S. So this is coming from the construction. Again, verify this. That for any X in the support of mu K, there exists a dyadic cube that lies in some dm, where m is between 0 and k, such that mu k of Q is equal to length of Q per S. So, I mean, let's see what happens. Yeah, so the question is, why is this true, right? So let's look at the construction in the like from the first step. In the first step, I defined mu K1 to be such that this condition is satisfied with mu K replaced with mu K1 for all dyadic cubes of length 2 power minus K. So in that level, it was this inequality is being held for all dyadic cubes of length 2 power minus K. But then I'm starting to renormalize, right? But when I renormalize in the second step, you see that I retain this guy if this is true. Yeah.
It makes sense. I missed that.
Yeah. And anyway, so I'll just complete this. So I retained this guy when this is true. That means for if Q is a dyadic cube that lies inside the first case, then for every child of Q, mu K2 of Q, sorry, mu K2 of Q prime, where Q prime is the child of Q, is exactly same as length of um, what is the sorry what is the name of Q prime? Yeah, the same as length of Q prime to the power s. And if that is not the case, if Q doesn't lie in the first case, then it lies in the second case, in which case mu K2 of Q is exactly equal to the length of Q. So in this process, you see that at some point, wherever the renormalization stops, that is a cube that I'm looking at. Yeah. So picking the largest cube, for each such x, we obtain a finite collection of disjoint cubes Q1 up to say QL that cover the support of mu k. Now I want to use this lower bound. Okay, so I have this collection that covers support of mu k, and our A is contained inside support of mu k. That means this inequality must be held, right? And that gives me a lower bound for the S sum corresponding to these QIs. Since they are disjoint, it's mu k of the whole space is the sum of the mu k's of QIs, and this is exactly equal to the sum of length of QI to the power S. And there was a slight mismatch between the sum we had over that was the typical S sum that had the diameter of QIs in it. So just moving on to the diameter. And we have a lower bound for the S sum from the assumption. So that's C, the lower bound, and multiplied by d power minus S by 2. That's positive. So you see that we have obtained a lower bound for the whole mass of mu k, a uniform lower bound that is independent of k. Okay. There is also a uniform upper bound. That's pretty straightforward because mu k of Rd is same as mu k of Q naught. And this, by assumption, is bounded above by length of Q naught per S, and that's anyway finite. Yeah. So we have a sequence of measures mu k's whose total mass is, bounded. And then, we use one of the compactness result, standard compactness results to say that you can find a subsequence of mu k's that weakly converge to some other measure mu, and this mu measure will satisfy the required conditions we need. Okay. In case you are not familiar with these weak conversions, the compactness results, I'll just state it here. You can look them up in any of the standard uh, textbooks in measure theory. So when I say weak convergence, this is what I mean. Its action on test functions converge to the action of mu. Yeah, standard of definition. And the compactness result that I want to use here is this: if mu i's so you need a uniform bound for the total mass of mu i's. Then this sequence has a weakly converging subsequence. Yeah. So using the uniform bound, I apply this theorem, and then I conclude that you can find a weakly converging subsequence uh, among the sequence of mu i's, and it converges to this new Borel measure mu. Yes, that's right. Compact set. Is that necessary to apply this theorem? That's not necessary to apply this theorem, right? Or am I missing something?
But difficult at that case.
Right,
There are some fixed number.
right. Oh, okay, right. So in this case, but I mean, I already have a lower bound. I mean, I already have a lower bound on the size of mu k's, right?
Yeah.
So wouldn't that imply, no, it won't, oh, only for compact sets. Yes, for compact sets, will be true. Yes, that's right. Thank you. So let mu be the limit. Then observe first that mu of RD, or rather mu of uh, Q naught is bounded below by the limit of these guys, the limit of mu k of Q naught. This is correct, right? Yeah. And this is bounded below by C times C power D power minus S by 2. And secondly, so it's not a, the measure that you've obtained is not a trivial measure. And secondly, the support of mu is now contained inside A. Okay, now here you have to use the fact that A is compact. Okay, and so please do verify all these things. And finally, the required growth condition. So you take, so here I'm going to look at balls rather than cubes, okay? So take a ball, let's choose n to be such that, let's say with r between 2 power minus n and 2r. And then we can cover this ball with 2 power d many dyadic cubes of length 2 power minus n. And then I can compute the measure mu k of this ball. So mu k, this ball is going to be bounded above by 2 per d times the supreme norm of mu k of any of the dyadic cubes that cover this ball. And we have already verified that for any of the cubes, this inequality is being satisfied. Yeah. And therefore, this is bounded above by 2 per minus ns. And well, just going to be lazy and then say that this is a constant that depends on d times r per s. Yeah. So with that, we have, okay, so this is true for all k, and therefore mu k, sorry, mu of is also going to be bounded by some constant that depends on d times r per s for all balls of radius r, and x can be anywhere in Rd. So with that, we conclude the proof of Rossmann's lemma. I started with a set of, a set whose S-dimensional Hausdorff measure was positive, and then using by in a step-by-step fashion, we construct a sequence of mu k's that were supported in the 2 power minus k neighborhood of the set. Then by taking the limit, we have finally verified that you obtain a measure that satisfied the required growth condition. Yeah. Yes.
So two questions. So one, you didn't Crossman measure. So we get a measure by constructing this, but is the measure satisfying the growth condition unique up to scaling or something like that?
Well, okay. So if this is true, then I can just, okay. So yeah, you wanted, I think the statement I mean, this constant must be equal to 1, right?
We
Is
get
that what you
one
mean?
measure.
Yeah.
What I mean is there a different a measure which is not equal to this, which also
Yeah.
satisfies the growth condition? Not
Yes,
equal to
it is possible. It's actually possible. Yeah. So it is not unique, as I said before. You can have other measures satisfying the same growth condition as well. Not just scalings. Yeah, yeah, yeah. Yeah.
Other question is, did we use compactness anywhere or just boundedness?
Yes, we did finally to verify. I mean, I've not checked that. So yeah, yes. To verify that the support of mu is contained inside A. So for that, you have to use compactness. Any other question? Great. In that case, let me just show you one application of Frostman's lemma. So when we defined the host of dimension, I intentionally did not talk about the product of sets, because typically we have this assumption that when I have a set of, in the case of full dimensions, this is always the case. If I have a set of dimension n and another set of dimension m, its product will give me a dimension of a set of dimension n plus m, right? This is unfortunately not true in the case of host of dimension. Okay. However, using Frostman's lemma, we might be able to show that we might be able to show that the host of dimension of the product is bounded below by the sum of host of dimensions. Okay. So let's see why this is true. So an application. All right. Let A be in Rn and B in Rm. The host of dimension of the product is bounded below by the host of dimension of A plus the host of dimension of B. The proof is, is something very intuitive. You take S to be a quantity, a value strictly smaller than dimension of A, and T to be strictly smaller than dimension of B. Then the S dimensional host of function of A must be infinity, or strictly positive. T dimensional host of measure of B is also infinity. So I can apply Frostman's lemma and then say that you can find two measures, mu supported on A and nu supported on B, satisfying the S growth condition and the T growth condition respectively. Yeah. Mu cross nu, sorry, and that's what I want to look at. But the conditions that are being satisfied by mu and nu are as follows. And R is positive. So I'm going to take the product measure. Sorry, this is nu, isn't it? Of mu and nu. Okay. And the product measure is going to be supported inside A cross B. Yeah. And if I'm going to measure the size of any ball, say centered at x comma y with radius r, then this is at most mu of the ball of radius r with centered at x times nu of ball centered at y with radius r. And from the assumption, this is bounded above by r per s plus t. So this new measure, the product measure, satisfies the s plus t growth condition. It is supported inside a plus b. And so by the mass distribution principle, or I think in Frostman's lemma, I've written it as an if and only if condition. So by Frostman's lemma again, I see that the S plus T Hausdorff measure of A cross B is positive. Yeah. Since this is true for any S smaller than dimension of A and any T smaller than dimension of B, we see that the dimension of A cross B must be at least the sum of these two. Yeah. So that gives you the lower bound for the dimension of A cross B. Are there any questions? All right. I was wondering if you're going to ask do we know anything about the upper bound to this guy? So clearly, you don't have you can't bound it above by the sum of dimension of A and dimension of B, but you can bound it above. Yes. So you can generally you can bound it above by the sum of the Hausdorff dimension of A and the upper box counting dimension of B. Okay. So in cases where the upper box counting dimension and the Hausdorff dimension of B matches, they are the same. Okay, so for example, when A and B are the Cantor set in any of the Cantor sets that we have looked at, then the dimension of the cross product is same as the sum of dimensions. So there are special cases where they are the same. But for that to happen, as I've said right now, you need the the Hausdorff dimension to match with the upper box counting dimension. So yeah, so that's one restriction that I have to impose on these sets. Okay. Yes. 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 There's also yeah. Okay, so with the remaining 15 minutes, let me just introduce a very closely related object of interest in this um, theory of force of dimensions. So far we have looked at two methods, right? As far as computing Hausdorff dimensions or Hausdorff dimension is concerned, if we looked at specific construction specific ideas through which you can compute the Hausdorff dimension. That was the Cantor set, right? Later we saw that by introducing a Frostman measure, you could then you could compute the Hausdorff dimension. The third method that we want to look at is the potential theoretic method. So here, instead of coming up with, so you can see that in Frostman's lemma, we wanted to introduce a measure that satisfies the ball condition, the growth condition for all balls of, a varying range of R. Yeah, so that's a lot of inequalities to verify. Instead of that, here we introduce something called the energy integral, which encapsulates this whole information and asks us to just verify the finiteness of a particular integral, okay, to talk anything about the Hausdorff dimension. So this is a widely used method in practice, and we'll begin by introducing the S energy integral. So let mu be a Borel measure, and S be positive. The S energy is given by this integral. I can write this integral also in the form of a convolution. So this is actually equal to the kernel Ks convolved with mu integrated against d mu, where Ks is the Rees kernel. So yeah, I think, yeah, okay, maybe I'll just try to state two results that relates the finiteness of the energy integral with with measures that satisfies the ball condition, the growth condition. Okay. Let yeah, let mu be a measure compactly supported and satisfying the growth condition. Then the T integral, the T energy of mu is finite for all T strictly smaller than S. Right? How do I prove this? I mean, I have to compute this guy. I'm going to decompose this. So yeah, I've assumed that mu is compactly supported. So yeah, I'm going to decompose this into what do I want to write here? I want to integrate it over aj of y, where aj of y is simply an annulus centered at y, whose width is roughly 2 per j. Okay. The collection of all x in Rd such that x minus y is roughly 2 per j. So it's between, say, 2 per j minus 1 and 2 per j. And since I've assumed that mu is compactly supported, I don't have to sum it over all j. I mean, I can assume that 2 per j is bounded above by the diameter of the support of mu. Yeah, so this sum is actually over all small values of j. I mean, all negative, I mean, essentially over negative values of j. So now what do I have? I mean, I can write this integral as bounded above 2 per minus js. And I'm going to just drop the lower limit here because I mean, the lower bound has already been used to pull out 2 per minus js out of the integral. And then I'll be left with mu of um, this ball of centered at y with radius 2 per j. And yeah, I mean, I'm pulling out 2 per j minus 1, I think. Right? So, I mean, I know that this quantity by assumption is bounded above by 2 per jt. Sorry, 2 per js, right? Okay, I got a bit distracted. I should be computing the t integral. So it should be t over here. And so this is bounded above by j 2 per minus j t is there. And this is bounded above by 2 per js. So that gives me t minus s. And then I have simply the total mass of mu. Yes. And this is, as I said, you are only summing over negative values of g. So this integral is finite, and that concludes the proof of the lemma. I mean, as long as t is, if t is strictly smaller than s. I think I'll stop here. So there is one more lemma that I want to prove, which will say that the converse of this lemma also essentially holds. Yes, that's correct. But 2 per minus j is 2 per minus j. So j's are negative essentially. I'm summing over small values of j. So 2 per minus j are yeah, so 2 power minus j are already large. Yes, 2 power minus j's are large. And t minus s is negative. Yes, that's correct.
No.
Yes. Yes, yes. Not necessarily, because j, as I said, so you can think of this as 1, right? So then I am summing over all negative values of j.
Why negative values of j?
Because see, as I said, you're considering small values of 2 power j. Yeah. Yes.
Why is this called an energy integral?
I asked the same question to sir yesterday. I think it comes from physics, right? I mean, I don't know, actually don't know the physical significance of these integrals. I mean, if I don't have the outer integral, the inner integral is a potential, right? The Newton potential, for example, something you must have learned in physics. But I don't know why, I actually don't know why it's called energy. Do you have any idea? No, why is it called the energy? Right. Can you use a mic? I think, yeah.
1 by mod x minus y power d minus 2 or something in higher dimensions.
Right.
Then
No,
it
but why is it called the energy?
So why is this called energy? Double
I think that's your question, isn't it? Yeah. Yeah.
But uh, our our Newtonian, I mean, our we have inverse square law, right?
Yeah. Yeah.
Is that by r to or whatever the
No, I mean, like, see, of course, the relevance of the integral as far as the, this theory is concerned, I mean, yes, I mean, that will be able to, we can see that, like, from this lemma, for example, and the converse of it that we have, I mean, essentially the converse of it. But I don't know the reason why it's called the energy integral. Yeah. Any other question? Is Rani still there online? I wonder if she has an answer to. Yeah.
No, I don't have. I don't have. I don't know. Maybe something to do once we do Fourier transform perception.
Oh, okay, right. Jyoti says, yeah, I think it comes from the notion of electrostatic energy with a given charge distribution. So there you go. Yeah. All right. I think we'll wrap up today's session, and I'll see you all in the next lecture.